Dear students, welcome to chapter 5. In this chapter, we are going to discuss about the concept of indexing used in DBMS. Before we talk about indexing, let us understand few terms that we are going to use often in this lecture. We are going to talk about an index file. We are going to talk about a data file. Now, let us see how a data file looks like. A data file is a collection of the tables, the records inside it. It can hold records of block of records. So data file at times becomes too huge to get it in the memory in order to run the database. For this reason, indexes are created. So now the index file is lot much more smaller than the actual data file, and then the links are made. It is easier to store an index file in the memory rather than storing the whole database. Now, whenever a particular field or record or a block is needed, a link which is connecting the index with the data file is used to bring the data from the data file into the memory by using its index. Now, so this is the data file. This is an example of a data file which is having the complete information about the fields in the record and the block of records stored somewhere in the disk or somewhere in the secondary storage. As we know, the secondary storage capacity is huge. It can hold lot of information, lot of data in terms of gigabytes and terabytes also. But the random access memory, which is used to execute the instructions, or which is used to hold the instructions that are executed by the processor, is much faster. It is expensive, but it is a lot more smaller than the secondary storage. So we have to store the database, a huge database, in the secondary storage in a form of files, and these files having the collection of blocks inside it. Now, when we want to run the DBMS or when we want to use the database, we have to pull in this information from the disk and put it inside the main memory for accessing it or using it. But as we know, the data size of the data file is much more bigger than, or at many times bigger than, the RAM memory itself. So what happens is now the indexing is going to help in this particular situation. An index is created and it is linked with the blocks. Like here you see the index is created and then it is linked with the blocks of data, blocks of records in the file, and then this index is moved into the random access memory, and as and when needed the data is pulled, or the part of the database is pulled in the form of a block, and then is moved to the RAM so that the database can be accessed for searching or for insertion or for deletion, for example. Okay, so we have to understand the data file. You know this. This is a data. This is an example of a data file. Index is, index file is lot much shorter than the data file. Okay, so now let us see what is an index field. An index field is a field in the table on which index is created. Okay, an index field is a field inside the records or inside the data file or inside the table on which the index is created, which makes it much faster or easier to search or access the database. Now let us understand, if you have a huge book, a heavy book, yeah, right? For example, you have the book for object oriented programming or the textbook for the database management system. And now if you are trying to search for the explanation of a particular term, so if you do not have an index, what will you do? You have to read and search the paper by paper. You have to search unless and until you find that word. So it becomes very difficult for you to read all that book at once. Rather, if we are going to use the page number from the index which is created, at the end of the textbook, so which is arranged in an alphabetical order, it will easily help you to locate the term because it is using an order. and you will quickly reach to that word, and then using the page number you can easily navigate it within no time. So indexing field is something like the page number, which is ordered according to the alphabetical order in the index. So now indexing field, did you understand? The indexing field is a field of a record on which index structure is built. Okay, now we will see what is an index structure. Okay, if we understand index structure, it is a data structure or a way of accessing the database in a faster way. Now, this index structure is built on, it can be built on an ordered file, or it can be built on an unordered file. Okay, for example, most of the time we use the employee number, and we can create index on an employee number in order to uh, quickly access the database. Similarly, an index can be created on a student number, which helps you to read the data, very fast, very quickly, because the numbers are arranged in a chronological order. Now, what is an index file? Index file is a secondary file. It is an extra file. It is a file that helps. It is an auxiliary file that helps to speed up the access of data in the primary file. Okay, so now what do you mean by a secondary file? Secondary file, it's like you have a data file over which you are going to create a second physical file, and this file is going to hold the index. So that is why it is called as secondary file. It is going to, now the index file is created on the data file, which is the primary file. Okay, how is this helping? Because the index is going to help you access the data files by using the index structure. Okay, now index structure is a data structure that helps for fast access. Okay, in our case, we said that if we have a huge textbook and you want to search for a particular term, then we are going to use the index pages that are made separately, which is going to help you to locate a specific term in the primary textbook, which is very huge. So this way the access of searching, the time for searching, the time for insertion and the deletion and for access become faster. Now think about a book, if a textbook, think about a textbook which doesn't have an index. So it will be very difficult for you to search things one after the other. Okay, so this is the concept of indexing. Indexing is done at two levels. Now what are they? Single level indexing, multi-level indexing. Now what do we mean by single level index? It means that you have a primary data file which is too big to get accommodated into the RAM, so we created an index. Okay, now this index is moved into the RAM, and based on the links, a particular block is accessed or brought from the disk into the main memory. So here there is only one index on the data file. Okay, this is called as single level indexing, wherein you have one level of index. But at times the data file becomes too huge, so you have to create an index on it, and index it also becomes too huge because if it is linking a very big database, for example. So the size of this single level index also becomes so huge that it cannot be kept inside the main memory. So we need to make an index over an index. Are we understanding? It makes over an index. For example, when you open a textbook, you see there is one index which talks or helps you to navigate the textbook based on the chapter. So for example, you have chapter 1, chapter 2, chapter 3, and the topics inside the chapter. This is your first level index. Okay, now at the end of the book, we still have one more index which lists the terms by the alphabetical order. So here we have index on index, right? So this is an example. This can be taken as an example of index on index. So we are actually using one index to refer to another index, and this index refers to the big data file. Now, what is the advantage of using index over index? Because the data file itself becomes so huge, so we make an index, but still this index becomes, bigger, which cannot be accommodated into the RAM, so we make another index on it. So this is called as multi level indexing, okay, which have multiple levels of indirection among indexes. So index, one index referring to another index may be referring to another one, and then the data file. Okay, so these are the terms that we are going to use more oftenly. I repeat, we talk about the data file, which is actually holding the records of data inside it, in a collection of blocks. The size of them is too much bigger so that we store them on the disk, but when they are needed to be accessed in form of insertion, deletion, or searching, we have to bring them into the main memory. Bringing the whole data file into the main memory is not possible because of the reason of the size of RAM is much more lesser than the size of the disk and the size of the data file. So we create an index on it. Index is now moved to the random access memory, and whenever there is a need for a data which is linked with the index or to a particular block, the block is transferred. Okay, so we talk about a data file, we talk about index file, and index file is holding the index field and the pointer. The pointer is actually linking the index with the data file. Okay, so we talk about two types of indexing: single level, multiple level. Single level means the data file is having only one index, okay, but at time, and this index file is moved into the random access memory. Multiple level indexing means you have a data file over which you have an index, because the index and the it's because the data file is too huge, okay, making its index also becomes huger. It cannot also be accommodated into the main memory, so we create an index on index. This is called as multiple level, wherein you have multiple level of directions or indirections among the indexes. Now let us talk about the single level index, or indexes that are used as an access path. An index is uh, just let me make sure the screen is recorded. Yeah. Okay. A single level index is an auxiliary file. Auxiliary file means it is a help. It's a file. It's a helpful file. It is giving you some help. Okay, which is actually stored in the disk in the form of a physical file. It helps you, or it makes it efficient to search for a record in a data file. Our index is usually specified on one field, although we can specify an index on more than one field. Okay. How is the index file created? One form of the index file is to create the entries inside the index file by using the field value, okay, and the pointer to the record. For example, we can use a field value as the name or SSN or as academic ID, and the pointer to link this with the actual block of the data file. So we are always saying that an index is created on a data file. How is it connected? This is connected by using a pointer. Okay, a pointer which will point or link the field in the index that we have selected with the data file blocks, okay, or the record directly itself. Okay, now indexes are always ordered by the field value. Okay, they are ordered by the field value. Now let us see we uh, how we access it. The index is also called as an access path on the field. For example, here is a figure wherein we have uh, k of I represents the field. Okay, k of I means it is a field uh, key value. Okay, a key value, and then a pointer to this I record. Okay, so this key I represents the record. So key value of the record is taken as a field value, and the pointer is going to link the field value with the data block. So in the table of index, or in the index and the entries, rather we can say index entries in the index file, is going to look like this, wherein we have a block anchor, which is the primary key value. Okay, for example, this is the name. Here it means that we have selected the name as a key field or as a field value to make our index, and then the block pointer which will link this name with the complete record which is stored in the uh, block, in the form of a blocks in the file. Okay, so let's move further. Okay, the index file, as because you see here the index file is only holding the key field, it is not taking all the information within it. So the size of the index file is much more smaller than what is occupied by the data file. Okay, so now it's like we have a index which is smaller. Now making an binary search on the index field will become more faster. Okay, a binary search on the index yields a pointer to the file record. Okay, so you can, for example, if I want to search, Noora, some girl Noora in the whole university, so it will, whole university, you can consider whole university as a data file which is very huge, and it will be very difficult for me to point her. So what I can do is I can go to the index which is having all the names arranged by alphabetical order. So this is an index. Now on the index, it will become very easy for me to apply a binary search and find out Nura. Okay. So just remember that a binary search on the index field will help you to link the key field. Okay, pointing to the file record in the data file. Index and indexes, there are two types of indexes. Okay, one is called as a dense index, another one is called as non-dense index. Okay, dense index means the index file have link with every search key value. Hence, every record, it's like, for example, you have a data file and you have an index file. Each entry in the index file is linking one record in the data file. So if you have 1,000 records in the data file, you're going to have 1,000 entries in the index file. This is called as dense. The opposite of dense is sparse. Sparse will have the index entries pointing to blocks or or only some search key values, not every value. Okay, in dense, the link is between every index entry with every search value in the data file. In the sparse, the index entries are only for some of the search key values. Okay, so these are the types of indexes. Okay, now here if you see, we have a huge data file. Okay, in the left side, you are going to see a sparse index because it is having, each entry is pointing to one block, pointing to one block, pointing to another block. So this data file is divided into 1, 2, 3 blocks. Okay, so each entry is linking to one block, or each entry is linking only to, few entries in the data file, and hence the link pointers or the field pointers are sparse. Okay, they are not dense, they are non-dense. Okay, now the opposite of it is like you have uh index, a secondary index. Okay, in this index, for example, we said that on a single table we can have more than one indexes, right? So here one index we made, the primary index we made by creating an index on the arranged or sorted IDs. Okay, so that I come here from the index, I am pointing to the first value in the block. Okay, and because they are arranged in the ascending order, it becomes easier for me to search for rest of the records in the block. Okay, so I make only one link entry. Okay, this is called as the primary index that we have made on the sorted IDs. Okay, the other way is that we are making one more index on the names. And you know, the names can be repeated. For example, we have a Mary Brown with a different ID, one more Mary on with a different ID. Now, when we make the index on, if we make a second index on the name field, it means it is going to repeat. So each entry in the secondary index made on sorted names are going to connect every record in the data file. So you see, Mary Brown is connected here, another Mary Brown is connected here, Ying Chen is again connected. All the files, all the index entries are connecting to each record in the data file. Now, the entries in the index of the dense index is equal to the records in the data file. However, the sparse index, okay, is going to have the number of entries equal to the number of blocks in the data file. Okay, now here is one more example. We have created a sparse index on name and dense index, secondary dense index on age. So sparse index is connecting, for example, this name is connecting the names which are arranged in alphabetical order. Okay, so you connect only to one of them, and then you want to search for Basu, you can just come and select the next record inside this block. So remember, the sparse indexes, okay, are created on sorted or ordered file. Okay, ordered file by name or by ID. In the previous example, we saw it. Okay, so this is the primary sparse index made on name. Okay, now why does it have to be sorted? Because each block has to be sorted so that the first, the link pointer points to the first entry inside or first record inside the block. Okay, and then from there you can search the remaining part of the block, remaining records of the block. So that is why the primary indexes or the sparse primary indexes are always made on the ordered file. Okay, you can make the file ordered based on its name or ID or any other field. In this example, we are seeing that the file is ordered by the name, because you see all things are arranged in an alphabetical order: A, B, B, and then C, then D, and then so on. Okay, now here it is having one more index which is created on age. Okay, now age is, for example, you see, they are the age is not a primary key here, so it is repeating, right? So the secondary index is connecting each entry in the index file with each record in the data file. Now let us talk about the indexes, the sparse indexes. Okay, the sparse index contains index records for few search values, or you can say the index entries in this sparse index connects to the or points to the block inside the data file. Okay, so that is the reason why the sparse indexes are much more smaller than the data file. Okay, now, it is applicable when records are sequential. Okay, now creating a sparse index is only possible when the records inside the data file are sequentially ordered on a search key. Okay, ordered file. Just we saw here that here the names were sorted. That's why we made a sparse primary key. The sparse indexes are also called as sparse indices. In index is also known as indices. Okay, so when you are trying to make a sparse index, okay, you have to make sure that the data file is arranged in a sorted way. And so that, we make the blocks and each block is connected with the sparse index entries. Normally, it will keep only one key per data block. Now you see it is having only one key per data block, one key per data block, one key for this block. Okay. Less space. It takes less space, can keep, okay. Now, the benefit of using a sparse index is that the index will take very small space, because you see here, if you have 100 blocks, okay, each block having, for example, 50 records inside it, the sparse index will have only 100 entries, okay. So the data file will be 100 multiplied by 50, which is like too much, right? 50,000 it will be. For 50,000, you have only 100 entries per block, okay? Each or 100 entries, because each block is connected with one entry, okay? Now, the maintenance overhead is less for insertion and deletion. Okay, insertion and deletion overhead is very less. Now, let us talk about single types of single level indexes. The single level, there are three types of single level indexes: primary index, secondary index, and clustering index. Now, a primary index structure is defined on a primary key, ordering key field. Okay, key field is nothing but primary key, right? Ordering, it's like used on the primary. When you create an index, okay, on the ordering key field, then it is called as primary index, okay. The field that is used to physically order records on the disk in a sorted file, a sorted way. The index has the same ordering as the one of the file. For example, here we have created a primary index on the file which was ordered by name. And in this example, we have created a primary index, okay, which was made on a sorted data file, which was sorted on ID. Okay, this is called as primary index. Okay, remember that primary index points to blocks inside the data file, and hence it is much more smaller. Okay, clustering. Clustering, okay, let us understand secondary index first. A secondary index is specified on any non-ordering field of the file. This is on the primary key is on the ordering key field. Secondary index is on the non-ordering field, means the file doesn't need to be sorted, okay. The field on which we are making the index doesn't need to be sorted, okay, and it can be non-ordering, so it can repeat also. The index has different ordering than the one of the file, okay. Now you see here, the data file is ordered, but the index is not ordered, okay. So this doesn't matter. The ordering in the secondary index doesn't matter, because here we are talking about non-ordering key field, okay. Age is non-ordering key field, okay. So each entry inside the secondary index will match or link one record in the database. For example, in the data file, for example, if the data file is having 50,000 records, then the dense index or the secondary index will have 50,000 entries. Now you see here, we have three records here, three records here, three records here. So we have like 9 records, and here how many we have? 1, 2, 3, 4, and then here 5, 6, 7, 8, 9. Okay. Here we have 8 records, and we have here 8 index entries. This is empty, so here we have empty. Okay. Clustering. Clustering index is specified when ordering field is not key field, okay. Is specified when ordering field is not key field, it is not unique. The index has the same ordering as the one of the file, okay. Now let us see what is clustering index. It says that whenever we have a field which can allow duplicate values, means a non-key value, not unique. So when you want to make an index on a key field which allows duplicates, okay, but it is ordering, but it is in the sorted way, then you make a cluster index. Index has the same ordering as that of the file, okay. An index file can have at most one primary index or one clustering index at a time. You either have a primary index or the cluster index. Now you see, students, the primary index and clustering index is doing the job of linking one index entry with a block of records in the data file. But the difference in the primary index and the clustering index is that the primary index uses ordering key field. Okay, ordering key field, wherein you don't have the repeated values. Like uh, for example, the block of records which are sorted by using the ID. Okay, the clustering index is also doing the same job of connecting one entry in the cluster with one block in the data file. But here it is not unique. It means the block can have multiple values, multiple same values. Okay. Now, at a time, we can have a primary key or a clustering, at a time, we can have a primary index or a cluster index on a file. We cannot have these two things together. However, we have seen examples. We have a data file on which we have one primary index and one secondary index. Okay, but we cannot have primary index and the clustering index at the same time on a given data file. Now, let us see let us learn more about the primary indexes. As we know, the primary index is defined on an ordered data file or sorted data file on its key field. Okay. Now, the index file of the primary index consists of a fixed length record. Okay, it's a fixed length record which is having two fields inside it. The first field is the same as the data type of the primary key. Okay, the first field is going to hold, for example, a primary key. Okay, and the second field is going to hold a block pointer. Okay, for example, like this, like this. Okay, this is the key field and the block pointer. Okay, like this. For example, a key field and the block pointer. This pointer points to this. Okay, so each one of them is represented by using the function k of I and a of I, where I is the block address. Okay, and k is the key and a is the pointer which is linking to this block I. Okay. Over here. Okay. Okay. I'll try to okay. I got this, recording thing on the slide. I was not able to see. Okay, now let's continue. Now, index. A primary index includes one index entry for each block. We know this, okay, and hence it becomes very shorter. The index becomes very shorter than the data file. Okay, the index entry has the key field value for the first record in the block, which is called as a block anchor. Okay, so for example, like this, this entry is pointing to the first record of the block, first record of the block, first record of the block. in all three cases, here and here and here. Okay, so and then this is called as a block anchor. This is actually linking the whole block. Here in this, in our case, there are only two records, but it can be 2000 records. So the block anchor is linking the block with the index entry, so that this the link is made here, and then any record in the block can be searched with the help of this block anchor, connecting it with the link to the entry inside the index. And so now I hope you understood what is a block anchor. It connects the index entry with the first record inside the block. A similar scheme can be used if we want the block anchor to become if you decide to make the last record as a block anchor. Okay, so in this case, your index entry is going to uh, point to the last record in the block. Okay, so last record also, this is also possible. The primary index is always non-dense because you are linking one entry with a block, so it has to be sparse, right? Since it includes an entry for each disk block of the data file and the keys of its anchor record rather than each record in the data file. Okay, here is an example of a primary index. The number of entries in the primary index is equal to the number of blocks in the primary data file. Okay, so we have a huge data file here, which is having one block, second block, third block, fourth block, fifth block, sixth block, seventh, and so on. And then you have index. Okay, now each entry inside the index, let me take a pen. Here, each entry is linking to a block. Now, this is called as block anchor. Okay, now this is the second entry inside the file, inside our index file, primary index file, which is linking to another block. Okay, and then it is pointing to the first one, which is a block anchor. Okay, so the number of entries inside the index is equal to the number of blocks in the data file. Okay, searching. Okay, once again. I am getting the search thing. Okay. Finding a record inside the, I'm not able to see because this zoom anchor is coming in the middle. Okay. Okay. Now, finding a record by using primary index is very fast. We do a binary search on the index. Insertion is easy because we have the key values in the records which are fixed length and they are arranged ordered in an arranged they are ordered in an arranged way, and then it is easy for you to search or insert or delete the records in the blocks if they are non block, they are not spanning. It means, like, for example, if the block becomes huge, it can span over the next block. Okay, so if this is not the case, then insertion and deletion is possible. Easy if the key value in record are fixed length and statically allocate block without block spanning. Okay, now else recomputation of in now if the blocks are spanning, okay, then you have to recompute the index for each insertion and deletion because you have to use the overflow buffer if necessary. Okay, so insertion and deletion is easier when the blocks are non-spanning. If they are spanning, then you have to recompute the index. Okay, So this is about the primary indexes. Now let us do an example here. Uh, if the data file of an employee holds, 30,000 records, okay, and each record is of size 100 bytes, okay. So the block size, for example, each block is holding 1024 bytes. Okay. Now let us see how we calculate the blocking factor. We know the blocking factor is the number of, the block size, uh, 1024 divided by the record size 100. It gives us how many blocks to store 3000 records. When the size of each block is 1024, we only need 10 blocks. Okay. So we need 10 blocks to store the employee data file, which is having 30,000 records when the block size is 1024. So we calculate the BFR. Now the second one is now number of file blocks. How many number of file blocks will be used in the disk? So it is given by B is equal to the record size divided by the BFR. So the R the number of records, sorry, not the record size, the number of record divided by BFR. So number of records are how many? 30,000 divided by the blocks 10. So we need only 30, 3,000 blocks to store this information, 30,000 information, 30,000 records inside 3,000 blocks when the block size is equal to hold 10 records inside each block. Okay. Now, let us compare the linear search. The linear search is given by the block, number of blocks, okay, divided by 2. Number of blocks are how many? We have 3,000 blocks, okay. So divided by 2 gives us the access time as 1,500 block accesses are needed. If the file is ordered and we apply a binary search on it, then it will be locked to uh, for the block size, 3,000 blocks, number of blocks. So we say log 2 number of blocks is 3,000. So log 2 of 3,000 is only giving you 12 block accesses. Now you see there's a huge, difference between 1,500 block accesses when you make it as, ordered file and apply a binary search. For an index on SSN, okay, assume the field size is VSSN is equal to 9 bytes. Assume the record pointer is holding 6 bytes PR, which is given by PR, and it holds 6 bytes. Then entry size, see, this is the data file, okay? This is the data file, and this is we are trying to make a index on SSN, okay? Now SSN is holding 9 bytes and the pointer is holding 6 bytes. Then the index entry will be 15 bytes, right? 9 plus 6, 15 bytes. Index blocking factor, BFR of index is equal to the block size, which is 1024 divided by R1. Okay, R1 is nothing but the size of each entry, 15 bytes. Okay, so 1024 divided by 15. How many blocks we need here now for the index to hold to this 3,000 blocks? We need only 68 indexes. Okay. Now searching on 68 will be much more easier than searching on, 3,000 blocks. So now let us see the binary search. Binary search is, for it's only 6 blocks. You see here we have 12 blocks, here we have only 6 blocks. Now, in order to reach to this binary search, first we need to find out the index blocks. Okay, so number of index blocks B is equal to R. Okay, R is nothing but the records, okay, that we have, okay, the blocks records divided by the uh, B, BFRI. So it's like 3000 blocks divided by BFR of I, which is 68. Now you have only 45 blocks to search inside the index, inside the primary index. So searching a record inside 3000 blocks, okay, in the data file is too much. However, if we search the index, okay, we have to search only 45 blocks. So the binaries, if we apply the binary search, it becomes very less. For example, we have log 2 to the 45, so which is almost around 6. We need one additional block to put we need one additional block access to access the data file. So this is 6 plus 1, 7. So, improvement again over uh, the ordered binary search. When we are trying to search from the index. Okay. So 7 is lesser than 12, right? So in this example, it is less, the difference is not much between 7 and 12. But if you increase the records, okay, so BFR will be higher, number of blocks in the data file will be higher, linear search will be higher, and then the binary search will also be higher. However, if you make an index and then you try to link this index with the data file, the searches in the index are much easier. Clustering index. The data file is stored on a non-key ordering field, okay, which is not having unique uh, you know a constraint on the field. It means it will allow to make a cluster index on a field which is non-key, which means duplications are allowed. Structure of indexes are similar to the primary index, but okay, but the two things are different. One is each index point to the first data block. Okay, so the block anchor is always first. Okay, the second one is sparse index. It is a sparse index, which means one index entry for every distinct value in the cluster field. Earlier, it was a block. Here, you have for each distinct value, you have a cluster field. Okay, so this is the difference. A file can have at most one primary key or one cluster key, but not both at the same time. Now, here is an example. Here we have how many blocks? We have one block, two block, three, four, five, six blocks. But now you see we have the cluster values not equal to the block values. Okay. Uh, don't- okay. So we just learned that in primary indexes, the entries in the index is equal to the number of blocks in the data file. But here we have the blocks based on the cluster of repeated cluster. For example, here we have one repeating three times. So we have one block, and then we have two here. Okay. And then here we have two again, and then, these are repeating, these are repeating. So for each block, we have a an entry here. Okay, for example, one is connect. All the ones are connected with the first one. All the twos are connected with the second one. All the threes are connected with the three, fields. So these pointers are pointing to the repeated cluster blocks. Okay, repeated groups, you can say. For example, we have a group of one, here we have a group of two, group of three. So each pointer is linking the index entry with the one group. How now the question comes, if you want to retrieve a duplicate value. Now, for example, if I want to retrieve 2 and the 2 is repeating and it is spanning over two blocks, so how do I do that? How will I retrieve it? In this case, blocks are consecutive to search. Okay, for example, you see the group of one comes followed by the group of two, then the group of three. So they are in the continuous way. Okay, so you search the first block. After you search the first block, then you try to look for the values in the next upcoming continuous block. Okay, so here, because the blocks are contiguous, it means one after the other, the retrieve become possible. So they have to be ordered. Okay, so it is ordering key, but repetitions are allowed. Primary indexes are ordering and repetitions are not allowed. Okay, so this is the difference. Here, we see the difference between a clustered or unclustered index. The cluster index is like we have a group of indexes, this is an index file, this is the data entry, this is the data record. So this is the index file and this is the data file. So we have one cluster pointing to one block or two blocks, okay, one block or so on. Whereas here in the unclustered indexes, we have each entry in the data file connected with more than one record. So this is the difference between clustered and unclustered index. Okay, now clustering indexes, insertion and deletion can cause problem when a block can hold more than one value for the cluster. Okay, so in the previous example, we saw that department number was repeating. Okay, now if we want to add one more, for example, a new employee comes. For example, if a new employee comes with a department one, then this two needs to be moved, and then this two needs to be moved here, and then this three needs to be moved. So this problem comes when we have insertion. Okay, it will change the index file, and it will, that changes corresponding addresses in the index file, and it needs reordering. Alternate solution is to, leave or allocate some unused block in each cluster. For example, we have a cluster here. We left one record. Now, if there is a new employee who is joining the company with a department one, it can be inserted here, and one more field can be left for that purpose, for the next time. Okay, so we can handle the problem of reordering by using extra space, but this creates wastage in the memory, because in each cluster you are leaving some empty spaces. Okay, so now, one more thing here, what you have to see is, for example, we have a cluster of holding three, but you see here, uh, even the empty space has been occupied. So we created a new cluster again, which is now being linked to the last entry of this cluster with the new, joining it with the new cluster. So this is called as a block pointer. Okay, this is called, yeah, this is the block pointer, which is coming from the index entry to the blocks, and then we have one more block pointer in the end of it, so that if the new records are added into the cluster, they are again kept connected with the next cluster. Insertion and deletion are easy. We don't need to worry about the changes in the index or in the block. So if you want to insert and delete, it is easier. We don't have to rearrange the things in the index or in the blocks. Okay. Now talking about the secondary index. Secondary index provides an additional means of accessing a file for which some primary access or primary index already exists. It is made on non-ordering field. Okay, non-ordering field can be key or non-key. Okay, So index in an ordered file having different ordering than uh, the two fields that you have selected. Okay, the first field of the same data file is as about the non-ordering field. Okay, and the other one is the block pointer or a record pointer. A file can have several secondary indexes in addition to the primary index. There is one index entry for each record, which makes this as a dense index. Index record points to the blocks in which the records are stored or to the record itself. Okay, so that's why it makes a dense index. We know the dense secondary index can be made on any non-ordering key field. Okay, for example, here we have an index file. It is this index file is linking to the secondary key field. Okay, now the point here is each entry inside a secondary index is equal to the number of records in the data file. Okay, so each and every value which appear in the primary data file also appears in the index. Okay, now for example, this is your index file, K of I, P of I entries. So we have index field value 1 through 24, and the block pointers are connecting with all 24 entries. Now here, this is the data file and this is the index file. If you create a secondary index file, okay, it might not be in the same order as that of a data file. Okay, and we have to remember that each entry in the file connects with each record in the data file. Okay, now let us see the access time when we are trying to search by using linear search. Now, considering the same example where we have 30,000 records, okay, and the record size is 100 bytes and the block size is 1024 bytes. The file has how many blocks? 3,000 blocks. 30,000 divided by the blocks 1024. So we have 3,000 blocks, okay, as we calculated in example 1 already. Suppose we want to search for a record with a specific value, okay, which is a non-ordering key field, okay, and the size is v is equal to 9 bytes. Without the secondary index, if we do the linear search, then we know that the linear search is v divided by 2. It will give us 15 block accesses on an average, 3,000 divided by 2. Suppose if we construct a secondary index on non-ordering key field, okay, where the block pointer is 6 bytes, okay, that we got from example 1, p is equal to 6 byte. Then we have for each entry r of I with the 9 bytes plus 6 gives you 15 bytes. Okay, and the blocking factor for the index is BFRI, which is given by the blocks. Okay, this one, the blocks divided by 15, which gives me 68 entries for each block. In a dense index, the total number of index Ri is equal to the number of records in the data file, which is 30,000. And hence we have 30,000 divided by BFRI, which is 68. It gives me 442 blocks. Okay. Now you see the difference because the secondary index In the secondary index, each index entry is connecting to each, record. So instead of like having 3000 divided by 68, which gave us 12 in the primary, in this primary one, 30,000 divided by, 3000 divided by 68 gave us 45 blocks. Here we have 30,000 records divided by 68. So this is the difference. Okay, so it gives us 442 blocks accesses. A binary search on the secondary index is going to be log 2 of 442, which is like 10 block access. A vast improvement over 15 block access on a linear search and 7 blocks access in the primary search. The difference is because the primary index were sparse and they were shorter. But here in the secondary indexes, they are dense and they are not shorter. So that's why we need 48 blocks in the length. Okay, so very important. And just try to solve it by changing the numbers here with, instead of having 30,000, you can consider a table of having 20,000 records and try to do all this again. A very important for sure question from, in the midterm or in the final exam. Secondary indexes on a non-key field will give, you know, many link connections. So when a non-key field is indexed, numerous records in the field data file can have the same value for indexing field. In this case, duplicate values need to be handled, and they are handled in one of the three ways: with duplicate index entries, variable entries, and extra redirectional levels. Okay, now let us see how to handle the duplicate index entries. Duplicate index entries with the same value, k of I, uh, is given by k of I. If a search key value appears 10 times, for example, in the data file, then there will be 10 entries in the index file. This would be a dense index. Okay, so binary search can become more complicated because the mid value can also have duplicates on either side. So we cannot, we have to search both the sides. Okay, insertion may need a reconstruction of index table because the index file is sorted. Okay. We are seeing an example of duplicate handling where we have, for example, 20, 10, 20, 40, 10, 40, 10, and this one. So we make an index. Now, the size of the data field is equal to the size of entries in the secondary index because it is dense. So each one entry is linked with the data file. Now I have this 10 connected to this 10, this 10 connected to this 10, okay, so on. The problem here is it will take more space to store the secondary index and it will take more time to search because we have duplicate values. Variable length records. We can use variable length records for index table in order to accommodate the duplicate value. Okay. So for a given record, for a given key, k of I, there is a set of address pointers instead of a single address pointer. So we have, keep a list of pointers for ki. For example, here, this is a key linking the data file 10 inside the data file. And here we have one more key with a 10 linking another 10. So now we can have only one entry 10 and then many pointers. One this pointer, another this pointer, another this pointer. So we have three pointers here. P1, P1, and then P2, P2, and then we have P3. Okay. So this is done like this. Okay. One pointer to each block that contains a record whose index value equals to ki. Okay. Now here the binary search becomes complicated because The midpoint addresses cannot be computed efficiently because there can be, multiple values in the middle itself. Insertion and deletion needs a reconstruction of the indexes. Okay, now extra redirectional levels. To avoid repeating values, we use indirections. What does this mean? We use most frequently used technique called as bucket of block addresses between the secondary index file. Okay, for example, we have here the secondary index one. For example, there's one here, there is one here, there's one here. So what are we doing? We are trying to make the link pointer of this one connect to a bucket. And here we are making the links as a, the collection of links as a linked list. Similarly, for the 2, we have a bucket to hold the pointers to point to the value 2. Okay, value 2. So we have only 2 here. The problem here is space may be wasted within the blocks. Okay, and this is the overflow, right? This is the overflow can happen. For example, uh, yeah, if the size of this bucket, you know, is fixed, then overflow will happen. Okay. Now, in order to handle, we can have, in order to handle the overflow of the buckets, we can have, linking or chaining of this again and again. Okay. So this is done. Want to keep your attention? Keep. Okay. Now, quick recap is indexing field is a key. If the indexing field is a key, we use primary index or we can use secondary index also. But if the indexing field is non-key, means the repetitions are allowed or a group of uh, values are allowed, then we use clustering. Okay. When we have a cluster, we can also have an index key on the non-key. So if you notice, the secondary index can be made on the key values or it can be made on non-key values. Okay. Uh, Whereas the primary indexes are made only on the key values. Clustering index can be made on non-key also. Clustering, if you try to make a cluster index on key, then it becomes primary index. So that is the reason why on a given table, we can either have cluster index or primary index, but not both at the same time. Okay. Now, some more properties of indexes. Primary index refers to the block of records in the data file and it is sparse, okay, because one entry inside the primary key is connecting one block and block is a collection of records. Clustering, also non-dense, okay, but it is going to hold the link between the clustering index entry with a distinct value inside the uh, you know and inside the clusters, inside the groups or inside the block. Primary key is dense. It means it will have each entry pointing to each record in the data file. One entry with one record, another entry with the next record, a third entry with the third record in the data file, and so on. Okay. This is the case where we have the secondary index made on key. But if it is not made on a key, it means the duplicates are allowed. So we have number of records B or number of distinct indexes fields. It can be dense or it can be a non-dense also. Wherever you are trying to link each entry with a block, okay, then you need to have a block anchor. So clustering has a block anchor, primary key has a block, a primary index has a block anchor, but secondary doesn't need a block anchor because they are already connected with each record. So no need of block anchor here. So we stop here and in the next class we will talk about
the multi-level indexing.